Hey guys. Well, thanks to Braden for that rather interesting opening. Good idea. I guess that means it's the last day of class. Good gracious. Okay, well, it's been really fun to talk to everyone about all of these topics in this discrete mathematics, but we're not done yet. Let's do some more. Let's do some more math. So I was in the middle of talking about graphs that could be colored in some way, where you color the vertices. We were talking about graphs that you could draw in the plane. Actually, that's a really fun topic to use for the last day of class. It's a really nifty concept. So, okay. Right. So last time I mentioned that there were some graphs that you could draw in the plane, right? And so that's called a planar graph. A planar graph is one which can be drawn in the plane with no crossing edges. So, it looks like my pen is not visible. How in the world did that happen? Just a second. So, let's go here, let's go here. Okay, I'm going to have to temporarily stop and restart the video. 1 second. Maybe I'll duplicate a moment. Okay, now I'm going to stop and restart this. So now let's do this. Let's add the camera. Here we go. Hooray! Does this work? Yes, now we can see. Okay, yeah, sorry. My laptop mysteriously ran out of battery a few days ago, and whenever I reboot it, I actually need to go and type a certain command to start the output to the screen. But anyway, okay, so we're here. Thanks for letting me know. Okay, right. So yes, planar graph means that you can draw it in the plane with no crossing edges. So let's do some examples. So for example, K3 is indeed it is planar because I can draw it in the plane with no crossing edges. That's okay. But then, you get some trouble soon because, for example, for K4, if I try to draw this in the plane, look at that, it crossed. Well, actually, that doesn't mean it's not planar. It just means I did a bad job. This is also a yes. Because the key word is that you can be drawn in the plane with no crossing edges. And so here we clearly did a better job. Actually, there's another way to draw K4 in the plane with no crossing edges. It looks like this. And this is why K4 is sometimes called the Citgo logo. Actually, no, it's not. It's usually called the tetrahedron. I think this is the Citgo logo, but I'm not sure. But in any case, this is often called a tetrahedron because you can think of it as a tetrahedron, which is just, drawn in this way. And then now how about K5? You could try. Uh-oh. Now what? How do you do that? I don't know. I don't know how to do that. But now the issue is this a proof that K5 is not planar? This is not a proof. In fact, if I want a proof, I need to try all the different ways of drawing this. So far it's unsuccessful, right? But maybe we can draw K5 another way. Maybe you can try to draw K5 with, I don't know, I'll put the 5 vertices here, and then we will do this first. As you can see, there's a lot of options. There's a ton of options because how do you even know the lines have to be straight, right? It could be totally nuts. So it's going to turn out that actually K5 is not planar. But in order to prove that it's not planar, it's not very easy to say, I tried drawing all of the infinitely many different ways of drawing K5 and I didn't find any. Because there's infinitely many ways, maybe. So what we're going to talk about is one of the fundamental principles in planar graphs, which ends up being a nice fact. So let me draw a planar, let's draw a planar graph. Here's a planar graph. I'm just trying to intentionally draw it in a little bit of a weird way where, actually it's not weird at all, but I'm just emphasizing that your planar graph can have random things sticking up. So if I draw this planar graph, this is planar because I have no crossing edges, I can think of the number of vertices. We know that from our graph theory. We can count that. Maybe we can count that. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. I think it's 9, hopefully. Counting is hard. Is that 9? Yeah, maybe. And then we can also count the number of edges. Number of edges. And how many edges do I have? Let's see. So I could say this is like 4 for that parallelogram looking thing, 5 for that stub, 6, 7, 8, 9, 10. And then now we can say f is the number of faces. And what I'm going to write here is in any planar drawing of a planar graph, something interesting is going to happen. How many faces are there here? Well, now here's where we need to define what a face is. Actually, in a planar graph, the number of faces is 1, because that's like the inside of something. You have like 1 face, 2 faces, and you always count the outside face as well, 3. And that's because you can think of drawing your planar graph on a very flat surface called the Earth. Well, no, the Earth is not flat, but the way you should think of it is that you draw your planar graphs on the Earth, and if you were to draw it on the Earth, there's this like outside, right? Like you can go around the other way. So there are 3 faces here. That's neat. And there's a very famous formula about V, E, and F, which you often find attributed to somebody named Euler. Euler is the same person who is attributed to this like most beautiful equation in math, this e to the power of pi times I plus 1. But Euler also has this other really powerful equation. It has to do with V, E, and F. And Euler's statement is V minus E plus F is always equal to 2 for every connected planar graph drawing. Okay, so I want to dwell a little bit on this. So the deal is, I said this is true for every connected planar graph drawing. The reason I said it has to be for the drawings is because if you have crossing edges, the faces are hard to define. Like the only notion of a face is if you can really say, I will connect these edges this way, and it's not like if I cut across, it's like, hey, look at that, I got some little triangles. No, this is like a legit drawing in the plane. And there's also this word connected. Why is there this word connected? Well, it's because it's just false if it's not a connected graph. So let me draw an example of something which is not V minus E plus F equals to 2. That one's easy. Let's just draw 2 triangles. So suppose my graph is this. Vertices equals to 6. Edges is equal to, each of the triangles gives me 3, so it's 6. And faces is equal to 3. Because the number of faces is 1 for the inside of that, 2 for the inside of that, and 3 for the outside. And unfortunately, V minus E plus F here is not 2. Over here, V minus E plus F is now equal to 3. So the important thing is that there's this wonderful Euler's formula for if I happen to have a connected graph that happens to be drawable in the plane, V minus E plus F equals 2. And has anyone ever seen that formula in a different context? Something that's not about graph theory? In fact, you often will hear about it as Euler's something formula, and that something is not the word planar graph formula. Has anyone seen V minus E plus F equals 2 in any other context? Ah, yes. Thank you, Eric. Polyhedra. Yes, because actually that's also why we call it the outside face. Let's go back to the tetrahedron, right? So if I had the tetrahedron, well, let me draw a better one. If we have a tetrahedron right here, this totally makes sense that you should say this has 4 faces, right? Because the 4 faces are sort of like the 3 faces that you can see here if this thing was spiking up for some reason. If this was like sticking out of the screen, then you have got these 3 faces here, and the other face on the other side it's supposed to represent like the underside. Or you could imagine if you put this tetrahedron on the surface of a sphere, right? Let me try to draw it a different way. If you try to draw a sphere, and this is going to be kind of hard, but if I try to draw a sphere and I have 4 points on it, which are on opposite sides of the sphere, then maybe on this sphere you have like this way, this way, this way, and then now you got to go into the back. This is like insanely hard for me to draw. I don't know how to draw this. But if you know what I mean, I'm like, that point is in the back. And like this thing here is also going to go around, and it's going to go into the back, and so on. And maybe this one goes around and into the back. Is that believable? Maybe you can sort of imagine that this is a tetrahedron. It's like a tetrahedron, like massively inflated into being on the surface of a sphere. And you can sort of see that if I took a tetrahedron and like blew it up, then I would actually have 4 faces, and that would be all of those 4 faces. And I also have the 4 vertices and 6 edges. So this is often also known as Euler's polyhedral formula, except that in the theory of planar graphs, it actually holds even for the connected planar graphs. And this is also showing some relationship between, hey, if somebody gave you a polyhedron, you could turn that into a planar graph. You can take a polyhedron and like redraw it in a way, and the way you do that is the same way you draw a map in the world. I mean, like when we look at any world maps, the world is round, the map is flat. But the way that we always make these map projections is we take round things and we project them onto flat things. So this is the connection between the polyhedra and these planar graphs. Okay, so now what I want to do first is I want to go about and try to prove this v minus e plus f equals 2, because that's neat, and that's going to be one of the ways that we go and show that certain graphs are not planar. How might you do that? Well, Advait, what do you want to do?
We use induction, maybe like on the number of edges.
Yeah, we want to use induction somehow.
Like you take a planar graph and then take off one of the edges and then it's still a planar graph.
Let's try that.
And then we show that like if v minus e plus f equals 2 holds on the smaller one, then it has to hold on the bigger one.
Okay, let's try that. I'll write for connected planar graphs. We'll have to be a little bit careful as we execute that, because there's the word connected in there. Okay, but we can do it. And the proposal is, let's use induction on the number of edges. And I want to get lots of people involved on this proof, so we're going to break this apart into stages. So if we're going to do induction on number of edges, I guess we need to have a base case. What's the base case? Well, the base case is a little bit weird because, you know, if I say my base case is there's just one edge, okay, but how many, like imagine I was trying to deal with 100 vertex graph with a whole bunch of edges. How do I reduce 100 vertex graph down to a connected 100 vertex graph with one edge? Well, there aren't any. So what I'm trying to say is that actually we're going to have a whole family of base cases. So we'll have a whole bunch of base cases. For each positive integer value of v, the number of vertices, right? That's the number of vertices. What's the base case? What's the smallest number of edges that you could have if you have a connected graph which has v vertices? 哲嘉. Yeah, if it's connected, the absolute minimum number of edges is v minus 1. How about we just like prove that one first? Okay, we're going to do that base case for every value of v, the e, which is exactly v minus 1. Let's prove all of those first. Anyone have any ideas on how I can prove that? So what I'm saying now is I'm just saying all I know is it's a planar graph and it has v vertices, it's connected, it has v minus 1 edges. So what does that look like? You're given, well, I'll use green because that's my base case. You're given v vertices, e is equal to v minus 1, and it's connected and it's planar. Now what? Do we know anything from our class? Isain. It's a tree. So now, good. So it's a tree, right? It's a tree because it has v vertices and it has v minus 1 edges. And it's connected. These were some of our conditions for the tree. There was like this thing we did probably at the beginning of the entire graph theory section. So that already we know that this implies it's a tree. Hey, if it's a tree, how many faces does it have? This is easy. One! There's only one face. Actually, if you want to know why, that's also because of the tree growing procedure. If you imagine growing a tree where you just keep sticking new things out, you're never going to close a face, if that makes sense. You just kind of have this spider going out, and you never close, right? There's no cycles. So actually, that's the easiest way to say it. There's no cycles, so there's no faces, except for that one big outside one. Does that make sense? Like that's nice. There's no cycles. So whether you talk about it from the cycle perspective or whether you talk about it from the tree growing procedure perspective, you get that there is exactly one face. Hooray! I know what is v minus e plus f now, because I have a v, I have an e, and I have an f. So then v minus e plus f is equal to v minus 1 plus 1, which is wonderful. It's 2. Great. So now we just dealt with all the base cases. So now we know that no matter how many vertices we have, if you somehow removed edges all the way down to this base case, now it's true. So now let's do the induction step. And now the induction step is, well, I have a number of edges. So I have a number of vertices, I have a number of edges, and that number of edges is actually strictly more than this base case. So I'm given a connected planar graph with, v vertices, no idea what that is yet, and the number of edges, my head's in the way, the number of edges is going to be strictly more than v minus 1, so it's just not one of those base cases. Okay. Now the goal is like, is there anything I could do to try to reduce this down to another problem that I can solve? And what Advait had said was, well, we could take away an edge, and if we took away an edge, if it was planar before, it's even easier to draw in the plane now. So if it's planar before, it's planar after. But I also need that it's connected. If I want to use this induction hypothesis, if I'm doing induction, I need to know, how do you know that if I have a connected planar graph with v vertices, strictly more than v minus 1 edges, how do you know that there's an edge I can choose to remove so that it's still connected? Anyone else want to help? Ising. Excellent. So the point is, that's where I'm using this, right? That's why I'm saying the E is strictly more than the V minus 1. Actually, that means that you definitely have at least one cycle. So, great. This piece implies that there's at least one cycle. So now if there's at least one cycle, let's just like break meaning take away. Let's consider deleting one of those edges from that cycle. And we were given a connected planar graph to begin with, right? So if we were given this connected planar graph to begin with, well, it had a cycle. Let's draw the cycle in the purple. It had a cycle somehow. But then it's like part of this, it's a connected planar graph. There could be more cycles, but it does stuff, interesting stuff. Maybe it doesn't have to go from there. I don't know. I'm just doing something here. Something. I just drew something, okay? So yeah, if you have something going on here, and there is at least one cycle, now what you do is you consider another drawing of a simpler graph where you just took away one edge. Doesn't matter which. Consider deleting that one edge. Well, I'll write after deleting one edge from that cycle, well, you still have connected, and you still have planar, because the drawing you were looking at, and you took away one edge. If there were no crossing before, there's still no crossing now. One edge from that cycle, still, it's connected, and it's still planar. Still no crossings. Okay. Now, how do I deal with this? So I'm like, well, if I did that, I can use this inductive hypothesis, right? So now what I found out is I have a new number of vertices. I have these new number of vertices, v prime minus e prime plus f prime. That is actually equal to 2 by induction hypothesis. I'll write the HYP here. Okay? Are people okay with that? It's like there's this new V prime. Whatever the V prime is, that's the new number of vertices. There's this new number of edges, which is what happened after I took something away. And I have a new number of faces. Okay. Why are we excited by this? How do you compare V's and V primes? How do you compare the primes and the not primes? Thomas.
Well, in the original graph before you deleted that edge, there's exactly one more edge, and there's also exactly one more face because there's one more cycle in these end up crossing.
Okay. So the important thing is you're like, what's the difference between the primes and the not primes, right? So there's the new V prime E and E prime and F, and there's the old V, E, and F. And we're kind of comparing them. That's why I drew it right underneath. That's why I drew the HYP over here, so I have the space. The new V prime and the old V, those are exactly the same. That's because I haven't done anything to the number of vertices, right? So from the new V prime to the old V, I'll write that it goes by plus 0. Is that okay? Like from the, there's no change. There's no change in the number of vertices. But what you also noticed is if I look at what happens to the new E prime and the old E, I drew this bracket thing because there's a minus sign, which is annoying. But I'm just saying if I simply compare the E prime and the E, well, to go from the E prime to the E, you go by plus 1. What you said is the opposite, but those are the same. It's a plus 1. Those are the same because what you said is like from the old picture to the new picture, you deleted one edge. So there's one less edge. And so if I have a true inequality, V prime minus E prime plus F prime equals 2. If I have a true equality, V prime minus E prime plus F prime equals 2, from that true equality, I know that E prime to this new, the new E prime to the old E, that would have been a plus 1. And then the last big observation was, hey, you know, by removing this edge, you lose exactly one face. It's sort of like you had these faces which were fenced in, and you broke a fence. So suddenly these two faces, whichever face this was part of, is going to merge with that one. Does that make sense to people? It's like if I break one cell wall or something, then I will have exactly one less face, because that was what was splitting apart two faces, one big thing into two faces. So the other important part is from the F prime to the F, that's also a plus 1. So now what I've just written is I have a known equality, V prime minus E prime plus F prime equals 2. And if I want to move to this V minus E plus F, well, the V doesn't change, and the E and F both move by the same amount, and they have opposite signs. One has a negative, one has a positive. So that forces that this is equal to 2 also. Did that make sense to people? I used white color because I wanted to show that's like how you deduce from the white calculations. If I knew that it was 2 before, and I adjust each of those values, where I adjust 2 of the values by the same amount, but they have opposite signs, then the sum is the same as it was before. Are people cool with this proof? Or if there are any questions, please feel free to ask. Because this is like amazing. We managed to just get a proof of vertices, edges, and faces formula, where all we did is we just used induction together with some tree stuff. And by the way, you can use this to prove Euler's polyhedral formula. That's a special case. I mean, the deal of like drawing octahedra, tetrahedra, icosahedra, your favorite hedra, like you draw any of those things, those are all planar graphs. And you can just use this fact to get them. There's a question. Subhashish. How would we know that the number of faces increases or decreases by 1? So we're talking about the from after deleted to before deleted, your faces is going to go up by 1. That's the same as saying the act of deleting an edge reduces one face exactly. And the way you know that is because, okay, here's this edge you're removing. There are two sides of that edge. And those two sides are in different faces. The reason they're in different faces, by the way, is because it's part of a cycle. So because it's part of a cycle, you can't get from there over to there. So my point is that every edge in a planar drawing where I have no crossing edges, in every such picture, every edge has exactly two sides. And those two sides are are in different phases because of the fact that there is this cycle here bounding it off. By the way, that question you just asked is extremely deep. That's a topology question. The real proof uses something called the Jordan curve theorem. It's actually not completely obvious that if I draw really wacky squiggles that there's an inside and an outside. I have just used that by assuming it's true. But that's what we will do in this class because we haven't taken topology. However, I think it's believable by most people that it seems reasonable. Okay, great. So now once we have this, we are ready to start drawing some interesting conclusions about graphs. Now, we will actually use this V, E, and F formula to go and prove that the K5 is not planar. However, in order to do that, we first need to we need to know something about the F, the faces. See, what I mean is like, one approach you might use is you might say, hey, suppose K5 was planar, then I would know something about the number of faces. Because if I have a K5, I know how many vertices there are, 5. I know how many edges there are, 10. And if I could do arithmetic, I'd figure out how many faces there are, but I can't do that. So we'll skip that part. On the other hand, that's not great because it's like, now how do I prove that you can't draw K5 with like however many faces? That's hard. So instead, we're going to do a different thing, which is an interesting way of counting things in two ways that lets you kind of get rid of the faces piece, or at least replace the faces piece with an inequality. So what I'm going to do is I'm going to, again, draw some graph. It might or might not look something like what I drew in the beginning, because I just kind of drew something. But this will be enough for us to play with. Stick something out there. Okay, so I got this picture. If I've got this, I'm going to say there's a really interesting fact. What happens if you sum, yeah, that's fine. Sum of all perimeters of all faces. Okay. Let's try to add them all up. First of all, I need to define what is a perimeter. Perimeter here is not like the actual length, because in graph theory, we don't care about how long each edge is. The perimeter is just going to count something like the number of edges along the face. So the perimeter is measured in terms of the number. Actually, I'm going to write the word in terms of, and you'll see why. In terms of the number of edges. Number of edges. And the reason is because I drew this in a funny way so I can give you examples of what perimeters are. So what do you think is a reasonable perimeter for that face? That's the easy one. That face. 5. Because it's like, look, there's 5 edges. That's 5. So this edge has, that face has perimeter equal to 5. Now it starts to get a little bit wacky over here. What should we use as the perimeter here? So I didn't want to say it's the number of edges because I want to think of it as like walking around inside. Okay? So if I'm walking around inside, I have 1, 2, 3, 4, 5, 6. Is that okay with people? I'm just saying like perimeter is called you hired an ant and the ant started crawling around and it crawled around on the inside and you just went to count how many edges the ant traversed. That's 6. So the reason I wrote down sum of perimeters of all faces is because there's some cool thing we can do with this. We can say it equals something. Anyone want to tell me what it equals? It isn't. Remember, I have vertices, I have edges, and I have faces. And I just found faces annoying. So I needed to do something with vertices or edges instead. How can I rewrite this? Shania?
It would just be 2 times the number of edges because you're walking around each side, quote unquote, of the edge.
Exactly. That's why we talked about this earlier. Every edge has 2 sides. And so we got this perimeter equals 5. And look at that. That goes around there. And that's why it's actually quite convenient that we can also have the outside face, right? The outside face is like going around the outside. And, oh, well, I'll just draw that for fun. So if I want to go around the outside, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the outside is the perimeter is 9. Is that right? Well, I see that they sum up to an even number, which makes me happy, and I hope that's right. Okay, good. So this is really nice. This 2e is the sum of the perimeters of all the faces. Okay, but my goal was to get rid of f. In other words, I wanted to show an inequality of some form. That's what we'll end up doing. We want to show some bound, because I can't say f is always something exactly in terms of the e and the v. But there's a really powerful statement we can write here, where I can write it's bigger. Oops, what happened there? I can write this is bigger than or equal to something in terms of f. And here's where there's one interesting insight. I want to say this is bigger or equal something in terms of f. If I'm saying I'm going to add up all the perimeters of every face, can you tell me that's always bigger or equal something in terms of the number of faces? We got lots of people. Braden. 3f, okay? So now the interesting thing here is I'm writing bigger or equal to 3f. Now, the important thing here is we got to be a little bit careful. It is true most of the time that it's bigger or equal to 3f. But it's not always true. There is actually a situation by which sometimes it's not bigger or equal to 3f. You see, where this is coming from is I think you're just saying like all the perimeters are at least 3. Like, they're all at least 3, aren't they? There is like a really weird bunch of situations when that doesn't happen. I see a raise hand question mark from Advait.
I was gonna say 2f because like double counting and stuff with edges maybe.
So double counting and something with edges, we got that from here. But I'm saying that Braden's is basically right. Like just about every face, every face has perimeter at least 3, doesn't it? I'm just saying there's like some weird thing. Chris, what are you thinking of?
So if you don't have any vertices, then in the case where then you have just one face.
So now what you're saying is that there are these really weird, mysterious cases which are just annoying, and that's correct. So if the number of vertices is 0, what's the number of faces? I'm not sure I have a great answer to this question, actually. The theorem that the v minus e plus f might not even be true if I have 0 vertices, but that's related to, if a tree falls in the forest, does it make a sound? Most people aren't very interested in the theory of graphs with 0 vertices. It's like, why are you doing graph theory? You got nothing there, okay? So let's think about graphs with a few more. But Chris's thing is there's still issue, right? What if you have 1 or 2 vertices? Could you say what you were thinking of, Aaron?
So with like one vertex, it's just like a single like vertex. So there's no edges, but there's still a face. It's like this kind.
Yeah. It's like there's one face, but what the heck is that perimeter? 0 or something? I don't know. It's just like weird perimeter, okay? Weird perimeter. And also, I think you said v equals 2?
Yeah, then there's only like one edge connecting the two. There's still one face. Like that inequality wouldn't hold either.
So this is weird. This perimeter is actually legit. The perimeter is 2. You see, if I look at this guy, there's one face, right? And the sum of all the perimeters is called just 2. And that's equal to twice the number of edges. This is actually true. Actually, it was also true up there. Weird perimeter equals 0. I'll just call it 0. And that's also sum of the perimeters is equal to twice the number of edges in both of these cases. But they're just stupid. Like, why would you worry about graphs with 2 vertices? The life becomes interesting once you go to 3 or more. So I'm going to write an important statement here, which is this is true if the graph is connected and has at least 3 vertices. Because, by the way, if the graph is not connected, I can also be like, hey, I can have as many vertices as I want. Bam! No edges. And that's also stupid. Like, what are you going to do with that, right? So the thing here is that we're going to only deal with connected graphs. So, Braden, I do want the 3f, but I'm going to write down that I specifically care about for connected and the vertices being at least 3 graphs. Okay, that's what we're going to care about for this interesting statement. It has occurred to me as I think this is true. I think I've managed to do this entire class without drawing a single sigma symbol. Is that true? I was talking to somebody else. I think I actually have not drawn a sigma summation symbol in an entire combinatorics class for an entire semester. And that's just showing you, that's because my standard style is like, I prefer to just show like patterns or write things out. And for me, whenever I see a sigma symbol, I just kind of like spell out what it is. And so here I have also refrained from drawing the sigma symbol just to like be complete with that. But you would normally write like sum over all the faces. Okay. Right. But now I have some really interesting thing. Wait. Oh, were there any for... Oh, no, maybe I'm wrong. Maybe inclusion, exclusion. Maybe I did draw a sigma. You have good memory because it's very hard to write inclusion, exclusion without a sigma. That's probably where we had it. Good memory. Okay. But let's finish this thing now. So we have this thing, and it's like, now I can actually say something about f. Or rather, I can say, if I don't like f is less than or equal to 2/3 e. I mean, I can just move the 3 to the other side. So what I've just found out is, so for connected planar graphs with at least 3 vertices, I know that the number of faces is less than or equal to 2/3 of the number of edges. Okay. Oh, and somebody said Genfunks, Vandermonde. I don't actually know if I use sigma in generating functions, actually. I always try to find patterns, but in any case. Vandermonde identity, maybe I did indeed use a sigma there. Okay, darn, I didn't make it through a whole semester. I'll have to try harder next time. Okay, but like as we go here, I know now something about the faces. So you know what? Let's go and start thinking about what else I could do. I know v minus e plus f. And I'll write then, for those connected planar graphs with at least 3 vertices, that's where we're working, I'll write the equation this way. 2 is equal to v minus e plus f. I like to do it this way because you can kind of like chain together equalities and inequalities. So 2 is equal to v minus e plus f. We had that before. And now I don't like f. So I'm just going to replace f with a less than or equal to 2/3 e. So I have a v minus e plus 2/3 e. Okay? And when you chain equalities, you're just saying like, well, something was equal to something, and then it's less than or equal to the next thing. So 2 is less than or equal to v minus e plus 2/3 e. But I'll write an equality. Let's simplify. So that's equal to v minus 1/3 e. Well, I think that's called e over 3. V minus e over 3. This is getting towards one of the important results, or nice results in planar graphs. I now have a relationship between vertices and edges. 2 is less than or equal to v minus e over 3. Multiply both sides by 3, and I'm going to use the, let me highlight which pieces I'm using. I'm going to use the 2, the less than or equal to, and the v minus e over 3. And the v minus e over 3. Right? I'm going to combine those things, and I will write down, that means that 2 is less than or equal to v minus e over 3. If you multiply both sides by 3, 6 is less than or equal to 3v minus e. And now you get this bound, which tells you like you're not able to have too many edges in a planar graph. That means that e is less than or equal to 3v minus 6. And the important thing is this is true for connected planar graphs with at least 3 vertices. I have this result. This is a common statement that you'll see if you look at graph theory books or anything about planar graphs. They will tell you that as long as you have at least 3 vertices and it's connected, then the number of edges is not that big. Because in theory, the number of edges could go up to v choose 2, which is quadratic in v. But for planar graphs, you can't get quadratic. Actually, it sort of makes sense, because if you're drawing a planar graph, if you try to be quadratic and you try to make like every vertex really connect to a lot of other vertices, good luck being planar. Because like you're going to cross stuff somehow. All right? But this is a rigorous proof that somehow, if you did it, your average degree would be like less than 6. That's actually what this means. I just made a statement which is like, this is kind of a cool statement. If I have that, if I know that my edges is less than or equal to 3v minus 6, the sum of the degrees is twice the number of edges. Let's continue with the corollaries here. Continuing. What I would know is that the sum of the degrees is equal to twice the number of edges, which is less than or equal to 6 times the vertices minus 6. And that's how you can see that the average degree, which is when you divide by v, is less than or equal to v minus 6. No. Divide by v. 6 minus 6 over v, which is strictly less than 6. That's telling you something about how if I have a planar graph, my typical degree can't be too big. And 6 is sort of like a limit. Okay.
6v minus 12.
Because I can't do math. Yeah, probably. Oh no! Oh no! Oh no! Oh no! Oh no! Yeah, no wonder people are making all these funny faces. Yeah, you see, you should. Thank you. Okay. Thanks, guys. Okay. There we go. Thank you. Yes. So arithmetic is hard. Algebra is hard. But now we're good. So the average degree is less than 6. And you know, if you read the course lecture notes, you'll be able to see like some bonus fact at the end, which is not required for the exam, but some bonus fact at the end, which is you can use this to prove the 6-color theorem actually. And the last time that I taught the class, we also didn't have time to go and prove that, but we threw that into the book anyway. Okay, but now like this is kind of nifty. The goal of what I wanted to close up today was now let's try to use this information to show that K5 is not planar. Any ideas? We'll actually show 2 graphs are not planar. One of them is K5. Advid.
We're just gonna plug it in.
Uh-oh.
Values.
How about K5?
5. Then we die.
Oh no! What is E? So I have E is supposed to be less than or equal to 3v minus 6, right? So I have a 10. And it's supposed to be less than or equal to 3v is 15 minus 6. No, it's not. Because 10 is not less than or equal to 9. Okay, so we have just managed to show that K5 is not planar. And that's quite satisfying. We didn't do it by trying all the ways to draw K5. That would be impossible. Instead, we did this by saying somehow, hey, we can count, like, have an ant walk around every face and count in 2 ways. And, you know, K5, it has at least 3 vertices and it's connected. Like, duh. Those are okay, so I can use this. All right. So that's one of these graphs which is not planar. There's another very important graph that's not planar also. The other graph that's not planar is called K33. And K33 is sometimes thought about as this problem of like having 3 houses and 3 utilities. Utilities. What are the utilities? Like electric, water. What other utilities are there? Gas. What's gas? Gas. Actually, that's probably not what you want gas to do. But anyway, these are the 3 things, okay? And so now you're supposed to draw these connections between them. And it's like everybody actually does want to have electric, water, and gas. And electric, water, and gas. And then this person is like, oh no, how do I get electric? I got my electric. I got my water. And how do I get the gas? I don't know. Okay, so this, by the way, is a proof of why you know that these utility lines are sometimes buried underground or sometimes on wires, because otherwise it would be impossible. Okay, anyway, so this is this K33. K33 is like 3 vertices, everyone needs to be adjacent to everybody else, and it turns out that this is not planar either. So it turns out that you can, that's like proof of K33 not planar. Well, how to do this? Let's try it again. Okay, I'm supposed to have edges is less than or equal to 3v minus 6, right? And the edges is equal to, what is it, 9? 3 times 3, 9. The number of vertices is 3 plus 3, which is 6. So I have here 9, and I have 18 minus 6. Yes! But no, but bad. Like, no, but no, that's not what I want. It's like, yes, but so what? The problem is that's not a contradiction. It's true, you know, like it's okay if the statement is true. You can have non-planar things satisfying this particular statement, right? But I need to find a contradiction somehow, and this didn't give me the contradiction. I wanted a contradiction. 9 is less than or equal to 12. So how do I get a contradiction? It turns out that the way you get the contradiction is, we go back and look at this. Suppose I had K33. I need something stronger now. Like this thing here where I wrote bigger equals 3f, that, yeah, I mean, it was true, but not enough. And I would love it if I could be more than 3f for K33. And notice I did weird stuff here where I said, you know, I can add some conditions. Like if it's connected and the vertices is at least 3, that's how I get my 3f, or else I'll be writing something less exciting. The claim is you can boost. There is a way to get more than 3f under certain conditions. And let's just let other people get involved. Thomas?
Well, in a bipartite graph, you can't have odd cycles, so you can't have, so it's greater than or equal to 4f.
Yes, let's use that. So the deal is like, if I'm just using a connected v at least 3, best I can do is 3f. But if I also know it's bipartite, then I get to say bigger equals 4f. Do you know what I mean? If I can say if it's connected, bipartite, and v at least 3, now suddenly at least 4f shows up here. Because the smallest perimeter is 4. It's bipartite. I cannot have an odd cycle, only even cycles. Okay? So the important thing, let's go back to next screen. So now I know, back to the sum of perimeters, which is twice the number of edges. Sum of perimeters. Now that's actually at least 4f for connected, bipartite, v at least 3. Okay, now let's use it. So now what do I know? This thing is first of all telling me an inequality about f. F is now less than or equal to e over 2 for that particular situation, because I just divide by 4. And now let's put everything together. Euler, and this is for connected bipartite at least 3 vertex graphs. Now Euler is going to tell me, Euler says, that 2 is equal to v minus e plus f. And then we continue this thing. That's why I like writing the line of equalities and inequalities. F is less than or equal to, f is less than or equal to v minus e plus e over 2. And that's equal to v minus e over 2. Now what? Well, let's take the parts I want to extract. And if I'll write down that again. So that's 2 less than or equal to v minus e over 2. Now you times 2 on both. 4 less than or equal to 2v minus e. Now I found out that e is less than or equal to 2v minus 4. And that's for connected bipartite graphs with at least 3 vertices. Is this cool so far? We've just used the same idea again, where we just said, hey, it's bipartite, so you can do this. Oh, now what happens? Well, now let's look at K33. The edges is equal to 9. The vertices is equal to 6. I have 9 less than or equal to 2 times 6 is 12 minus 4. No! That's exactly what I wanted. That's a contradiction. So, contradiction. And that makes us happy, because that shows us that somehow the K33 is not able to be planar either. Okay, so now what we have just found out is that there's like these 2 graphs we've just found, K5 and K33, which are not planar. Why don't I just do this for more and more? Well, it turns out it's because there's a very famous theorem, Kuratowski's theorem, which you will actually see a proof of, I believe, in the graph theory class at CMU. Kuratowski, and we won't prove it in this class, but Kuratowski's theorem actually tells you if you have a graph that's not planar, you can find a K5 or a K33 in it somehow. But possibly like stretched out. Okay? So every non-planar graph has a subdivision of K5 or K33. That's why we bothered to just show these 2. What's a subdivision? I'll just draw a picture. A subdivision is something like if I had, and here I'm going to draw it in a not planar way because it's not planar, right? So I'm going to say it took a while to get there. Let me circle the vertices of the K5. Sometimes I got lazy and just go straight, but in general, everything got from everywhere to everywhere. Whoa, I'm only supposed to connect to the ones that are circled. And then this one maybe goes here. Now I'm lazy, I'm just going to connect them all. Maybe I make that guy go. Yeah, it's good. Does it look like a K5? It looks like a K5 just with like some more vertices on the way. And the point is, like, it turns out that if a graph is not planar, there's something like this in it. And like, that's satisfying because I know that one can't be drawn in the plane because the K5 couldn't be. If you can't draw the K5, good luck drawing this thing. It's basically a K5. And so that's why the work here was just to show K5, K33 not planar, and to complement the other side, if it's not planar, turns out one of those is there. But that's a tough theorem. Advait, did you have a question, or was that from previous?
Like, in order to go from subdivision to subgraph, can you just take all the degree 2, like, vertices and then just, like, delete them out, kind of?
Yeah, so you're thinking of like, what is a subdivision, subgraph? Yeah, it's something like that. But the only difference is I want to say that sometimes you contain the subdivision, but you don't contain the subgraph. Like there's no,
That's
yeah.
what you can transform from the subdivision to the subgraph.
Yes,
I like the stuff.
yes,
Delete all the degree 2, vertices.
yes, that's the general idea. So thank you for asking. But so that's just why I wanted to close on this. We have just managed to prove some interesting things which connect between like mathematics, actually some ideas from topology, but that's a good place to end the class. So I just want to say I've been very impressed by everyone I worked with this semester. It's been very interesting to be able to talk to you about all these different topics in combinatorics. My hope is that what you've learned from this is not just how to do particular problems, but how to think and how to like invent new ways to solve. That's why all of the exams have weird problems. They're all about like, and all the homeworks, everything is not exactly the class because the whole point has been to teach people how to invent. That's also why the way I taught the classes, I sort of intentionally try to just have a theorem we want to talk about and let you guys bring out the idea and we improvise together because the whole goal was to hopefully have everyone learn how to invent. With that, thank you to everyone. Have a good luck on your final exams. Bye-bye.